Hi, and welcome to another Hopper video. Hopper is a modern semicolon and curly brace language, but designed for small devices. And this video is about a small device. This video is about writing a Hopper compiler for the Z80, Z80 microprocessor. Once again, I used this 8-bit force retro shield. And which one do we use? The Z80 one here. So Z80 retro shield from 8-bit force. I've done a lot of explaining about how this all works in the 6502 playlist, so I'm not going to repeat myself here. Suffice it to say, it's a very sort of approachable way to get a Z80 running. So you don't need to own a Z80 machine. You can buy all this stuff and get your Z80 running sort of in a bottle on top of a Arduino style microcontroller. If you've been following along with what I've been doing up to now, you'll recognize this Mandelbrot. On the right here, it's running inside my Z80 emulator, which I use to test and debug my Z80 Hopper code. And on the left here, it's running on that device on the Tindie that's hosting the retro shield. So this is the serial port connection to it. Anyway, let's get back to the topic. So, I wanted to write a compiler that actually generates native code for a change. Most of the time, I'm writing runtimes. So, like the 6502 one, I wrote a Z80. I wrote a 6502 runtime in 6502 assembly using my tools, but it was still running Hopper programs in Hopper bytecode. This time, I wanted to try writing a native code compiler to actually write Z80 code and run the Z80 code. But I didn't want to rewrite the Hopper compiler, so I wrote the process of generating the Z80 code is as follows. It runs the regular Hopper preprocessor. It runs the regular Hopper compiler. It runs the regular Hopper optimizer, and at this point we've got Hopper bytecodes, Hopper virtual machine bytecodes. At this point, this is really where the compiler is, and it's really translating Hopper bytecodes into a Z80 assembler. After which I optimize the Z80 assembler. And then this code generation part at the end isn't really code generation. This is where I convert the Z80 output, which is actually in a Intel iHex format so that you could burn it into a ROM. But I just convert it at that point into sort of a C hex image of that ROM that I can paste into the Arduino IDE and get into the retro shield environment. In this format, I'm emulating my favorite serial chip, which is the Motorola 6850, to provide the connectivity between the Z80 and the outside world. And I'm also emulating the same way I do time on actual microcontroller board. I mean, actual microprocessor boards with, like with the VIA on the versatile interface adapter on the 6502 provides time in milliseconds in 4 0-page slots. So I do the same thing, but I use the Arduino millis to simulate it. So that's how I'm simulating the peripherals for this device here. And yeah, it gets its RAM and ROM from the Tindie in case you haven't watched those other videos. Anyhow, let's get back to the problems. So to generate this code, I wanted to support the entire Hopper minimal runtime, which includes the string type and also the array type. And Hopper does garbage collection. It's a modern language when it comes to memory management. And the way it does this in the usual Hopper environment is it's a stack-based machine of the simplest type, and it's single-threaded, so that means that the stack itself is a live list in your garbage collector. If you can't reach it from the stack, then you should collect it. And it also does reference counting. The Hopper stack needs to support more than just the minimal runtime, which means it needs to do runtime type management. You have to do that if you want to support things like variant types, where you don't know what the type of the stack slot is going to be at compile time. For the minimal runtime, thankfully, it only supports strings and arrays as the only two reference types, and neither of those can contain other reference types in the way that a list or a dictionary could. So it simplifies the memory management a little bit. You've only got two reference types that you need to manage. So what I decided to do, let's get to that. So another thing I wanted to do with the Z80 is it would be crazy to simulate the Hopper stack on the Z80 in terms of both size and performance. So to build an artificial stack on top of the existing 8-bit microprocessor, I wanted to see if I could use the built-in hardware stack this time around. Because with the 6502, I did do that. I simulated the stack because I built a runtime rather than a compiler. So with the Z80, I wanted to see if I could use the hardware stack instead, directly use the hardware stack for the Hopper stack. This comes with a couple of problems. The easiest way to build a stack machine, a virtual stack machine, is to have two stacks. So you typically have one stack for the call stack. So it's typically used for the return addresses from methods and for maintaining the stack frame, which is also known as the base pointer. So you push and pop that as you enter or exit your method. You maintain the stack frame. And you do that on your call stack. And then if you have a second stack for values, it makes the implementation so much simpler. So the values would include arguments being passed to your methods and any local variables declared inside that method. And that allows you to use, the reason you want local variables in there is so that you can do recursion, for example. Why does that make it simpler? Well, if you do it that way, you don't have to sort of pussyfoot around how you deal with, not damaging the return address. And also the result value you can push back on the stack without worrying that it's going to, you don't need to make sure it's before or after the return address. You don't need to do the gymnastics of working around the return address. And it also allows you a simpler implementation in terms of cleaning up the stack. So with this implementation, you can make the callee rather than the caller clean up the value stack. So the caller is responsible for the call stack, so the return addresses, and the callee deals with the value stack. And like I said, it's easy to return the return result of a function call or an expression on the stack, because you don't have to. Yeah, it's much easier to maintain. If you want to have one stack, though, if you want to use the Z80's actual machine stack, you can't do this. So in order to support this, I needed to make changes to the Hopper environment so that I could still keep the whole Hopper environment and just make it so that the code it was going to push out at the end of the day was going to be more friendly for a single stack. So a couple of things I did to support that. I added a second calling convention to the Hopper environment. So that same calling convention works on all the different Hopper environment platforms. So it's sort of similar to the CDecla calling convention. And all it is it's a change so that the caller is responsible for the arguments on the stack, not the callee. So the callee is obviously still responsible for the locals. Another thing I changed is I added a register to the Hopper virtual machine for the simple purpose of returning the results of a function call. So at the end of a function call, puts the return result into this register, and then whoever called it can pull the value out of the register. And this just untangled the return value from a function call from the maintenance of the call stack and the frame and the stack frame. It did mean that this return register also needs to be considered as from the regular hopper garbage collection. It needs to be considered as part of the live list. But it's greatly simplified the stack behavior. So yeah, to go to a hopper compiler, I didn't want to do the reference counting or runtime type checking in the compiled code. I wanted to do it in the compiler. So during the compilation process, as it is walking through hopper bytecodes in a method, it's keeping track of where the stack pointer would be and what the stack slots are and whether they're reference types or not. And if they're reference types, it does the reference counting at compile time. So it makes the compiled code simpler, but it makes the translator that's translating these two things a little bit trickier to do. Anyhow, it sort of all worked out. So that reference counting has been done in this translation here. So once it gets to the optimizing and the code generation, it's completely unaware that that's even happening. And that allows me to do the sort of modern version of garbage collection in this compiler. All right, let's get to... So there's a recent release on the GitHub for this Z80 update, which includes all the latest tools. So that you can actually do this without needing a Z80. You could do it on Windows. If you run through that 6502 playlist that I mentioned earlier, you can see how to get this all set up on your Windows machine. And one of the things you get on the Windows machine is this emulator. So let's play with it a bit. So if we edit test here, let's do the usual hello world. Let's switch to a full screen here. Right. So yeah, they recently decided to discontinue these dip package, the 40-pin Z80s dialog. They're no longer going to be making them. If they lasted till next year, it would have been 50 years. Actually, I think it's 76. It would have lasted 50 years, but after 48 years of production, they're ceasing production of the chip. Anyway, okay, so what's Reitlin? Reitlin is it's the same as Printlin, but via the serial port. And in the Hopper minimal runtime, most of the runtime is written in Hopper code. So the only part that's not written in Hopper code, I'm right-clicking on things to navigate, is like write a char, read a char, and is there a char available? So there's 3 little system APIs. Okay, so if I press F7 to build this, if we look at the bottom of the screen, we'll see the different steps here. It'll zip through them. There they go, pre-processing, compiling, optimizing, code generation, optimizing again, etc., etc. So it's generated our assembly for this. We can go and have a look at it. How would we do that? Let's look at more. Debug. Test. This is the assembler listing. Yeah. So I try to make it efficient, but there's certain things I didn't take advantage of yet. So as it enters the code, Z80 ROM starts at 0. That's the entry point. It disables interrupts, sets up the stack pointer, and then just calls your hopper main. And if you ever exit hopper main, it just halts. Then I had to leave some space here. Oh, I do leave a clue to the... This is a clue to the disassembler, actually, to tell it where the constants are. They start at C15, which we'll see in a second. I have to leave this space here because let's do that again. It jumped past. I got 2 clicks out of that. Come on. I'm going to make a smaller version of this because it's too much to try and explore. Let's make a smaller version. Let's just, for example, do this for now. Serial right car. Let's just put out a bang. It's easier to explore the assembly if there's less of it. Okay, here we are again. So why did I need to leave all these zeros here? Because at the hex 38 address is where the interrupt service routine for the regular interrupt is, the maskable interrupt. And in this case, this one is handling the serial port. And just below it has NMI. So at 66 in interrupt mode 1, 66 is where the non-maskable interrupt is as well, and I wanted to put a return instruction in for that one as well. And then, just like the Hopper compiler, the Z80 compiler for the Hopper language only includes bits of the runtime that you're actually using. So we called serial write char, so that bit of the runtime is actually in use. And then we immediately got to, and then there's no constants, but it's got a little placeholder with a size. Again, it's not entirely optimal, but it's good enough. And then we enter the Hopper main, and all it does is calls this serial write char at the bottom here. So it loads up 21, which is the bang, and makes a call to serial write char. So it's using the regular Z80 stack quite effectively, and this is relatively small. So if we go Z80 disassemble again, test, that's 181 bytes of code. Sort of the minimum implementation. As soon as I put that string back, let's build that again. And let's see how big that was. We went up to 3.5K. And that's because it's including a lot of the runtime to do that. So it has to include memory allocate, memory free, garbage collector release, garbage collector create, and a bunch of different string methods. And we can see which string methods it's going to include. So it's going to include writeLin. So let's right click on that. So inside writeLin, it used string new. It's going to use this one here where it writes out a string and steps through it. So let's go and check that out. So that's this one here where it steps through the string, and that's going to need to include string length. And here it's going to need to use string get item for this. So a fair amount of string APIs and string new and string clone, because the way the stack works is a strict copy on write. So there would be a copy. Would there be a copy on write? No, probably not, actually. You just push it off the stack and print it. Anyway, that's the code for this. So let's just run this Hello 1976 on the device, shall we? So one of the things that the disassembler does is it creates a ROM image. And I've got another editor open here. Let's see if I can get that quickly. And we can make it tiny as well, because what did we say it was? Oh, it's 4K. It's going to need 4K, so 4K ROM. It'll warn me if I've gone over my ROM. So let's do that. And if we switch back, let me show you the full screen again. So I'm back in the Arduino IDE. Let's clear the serial. Let's go to the ROM image, and inside this ROM image, it was an 8K image. So let's do paste in there. It's now a, what's that? 4K image, yeah. And I can burn that to my Tindie. So that's uploaded it onto my device, and there it's booted it up, and it's immediately got to Hello 1976, and immediately halted. So not a very exciting program. I guess we could make it slightly more interesting. We could put it in a loop. So hopper loop, which will loop forever. And we should probably do a delay here of, say, delay seconds. Can we delay seconds? No, let's just delay like that. Delay for, say, 100 milliseconds. Let's see what that does. We compile that again. Does it still fits inside my ROM? Yeah, quite a bit of room. So let's paste that in here again. Upload again. And there we go. So now it's pumping out Hello 1976 at 1 second intervals, and it'll run forever instead of just exiting after the first run. Anyway, you get the idea. What should we look at for that? We could go and have a look at what that method actually looks like, and I think I'll just load it in the editor. It's easier to navigate. So go to load the listing. And let's go and look at there's the right line. You can see right line, right, all these different methods that it's included. What are we looking at here? Right. Actually, I'm going to get rid of the video. There we go. And let's switch to full screen. So no syntax highlighting, unfortunately. So here we go. Here's the main method of Hopper. The main method, and here it is where it's calling right. So yeah, these are all the other methods it's had to implement. That's why it got to 4K. But 4K is still pretty impressive. I remember the Turbo Pascal minimum runtime was about 10K. But that, I think, did a lot more than what this one does. Well, maybe not. Didn't have that much more fun. Oh yeah, they had math functionality in there, like floating point math, which I don't. Here, yeah, it did a lot more. So you can see the different... in the assembly, it's showing you the original source code that generated this code. So for each line of Hopper, so line 12, line 13, line 14, some of them generate quite a lot of code, because this one has an expression in it where it creates a string, new from constant, and then it calls right line. And then after it comes back, because the caller is managing the stack, it needs to call release on that object to release the string that it created on the stack. So that's what this code looks like. But it's fairly dense. This is fairly dense code. So it means that when you write bigger Hopper programs, you're going to... And another interesting thing, if we stop that from scrolling, let's switch back. If we look at the amount of memory, because I only used 4K for the ROM, I have 60K of RAM available in the memory map. So without doing any bank switching or anything, I can write quite a big Hopper program that'll fit into 60K. Yeah. And it's calling jump subroutine here. Oh, no, jump relative, sorry. So right at the end of the loop, it's just jumping back up to the start again. Up to where was that address? What's it jumping to? Z80. So, it's jumping up to here. Back up to here. Yeah. Yeah, there you go. What else can I show you? Oh, the emulator. Yeah, let's load this in the emulator. So the emulator, Z80. I want to pretend instead of a serial port, I want to pretend it's in a terminal window, like so that we only need one window open, and we want to load test. So it's loaded that into the emulator. If we look at the source code, it's sitting at address 0, waiting to execute. So I can step through there, disable interrupts, set up the stack pointer, and then I can F11 to all the instructions are as usual here, and there's shortcut keys. So I can step into my main method, show the source. So this is all the preamble. So there's quite a lot of initialization that needs to go on. Set up the correct interrupt mode, load 0 into the accumulator, and then it stores 0 in a lot of places. And what all this is actually initializing the heap, the free list in the heap. So let's get beyond that and enable interrupts. And then these 3 instructions set up the stack frame, because I use the IY index register as my base pointer for the stack. So the actual stack pointer, SP, is the stack pointer, but my base pointer for my frame, for my stack frame, is IY. And that means I don't use IY for anything else, just for that, because it's a stack-based language, so it's so intensive in terms of use that it's worth reserving that register for it. And here you see where the source is mapped into the actual Z80 code. So in terms of trying to debug Z80 code, this will debug any Z80 code, not just mine. But if you're debugging mine, it has the it knows a bit more about what's going on. So there's no local variables, but if there were, it would show them in the value stack here. Actually, let's step. So if we look at the heap right now, there's no heap. It's all free. It's all in the free list. So let's set up our stack frame. We've got our stack frame set up. So now we should see base pointer. Yeah. So we see base pointer here in that list. And it annotates the return addresses too in the stack, so it shows you what's going on. Now we're going to load up the address of this string constant and the length, and then this call here is to create a string from a constant. So let's do that. So now we should see it on the heap. There it is. It's on the heap, but it's not on the stack yet. So there's a little bit of homework being done here. And we just pushed it onto the stack. So now it should be on the stack. So 102, 1002. So the first address is the size of the block in memory. The second address, 1002 here, is the actual string. So the string is now on the stack, but it's anonymous because it's not being put into a variable. Let's keep stepping. This is incrementing. That's incrementing the reference count for it. And then this call here should be the one that's calling to the function that calls the other functions, like it's all the hopper runtime to display a string at the serial port. So let's F10 that, and we just should see it do all the work. There it is. So F10, and we got a hello 1976. Anyhow, these are the tools. So there's a few more tools. Let's quit out of this. So if we look dir of bin and CA, like that, what are we going to see? Yeah. So the tools that we have is the generator. Actually, we just want to see the hexes, so that didn't work as well as I'd like. Yeah. Okay. Anyway, the hexes are the optimizer, the generator, and the disassembler. There's three new tools, and then the tool I'm using right now is the other one, which is this thing here, Z80, which is the disassembler. Right. I think that's all I can say about writing a Z80 compiler. So I can write more about this. Depending on how much interest there is. And I can highly recommend using these retro shields. So from 8-Bit Force. That's a really easy way to get yourself a Z80 machine up and running without actually having a Z80 machine. So thank you for watching. And I think that's going to wrap it up for me for the Z80 compiler.